So for number 9, they want us to take the area bounded between these curves and then revolve it about the x-axis like so. So I've gone ahead and I've drawn these curves, and for the one in orange, the xy is equal to 1. If we divide both sides by x, that's just the rational function y is equal to 1 over x. So what happens when we revolve this around the x-axis? Well, it's like we're taking a chunk here, this little height, and this height is basically just wherever it touches the curve, right? It's the difference between 0 and that curve. And then we're going to revolve it like so, and this is going to give us a cylinder. And the cylinder, it's like an infinitely thin cylinder, and when we open it up, it basically, it's sort of like a sheet of paper, right, that we have wrapped around the x-axis. And the sheet of paper, it has an area. And so if you, maybe I'm going to draw this in a different color. And so as we move upwards, we're going to have different cylinders. They're going to go like something like this. Yeah. And so there are a bunch of cylinders that get wrapped around this curve, right? And that is going to give us a volume. So before we do anything, let's set up the integral for the volume. So basically the volume is the integral of these areas. We're summing up these areas, and these areas are a function of y because we're summing them up vertically, right? We're summing them up from y is equal to 1. This here is the lower boundary all the way out to the upper boundary. So we're summing them from 1 to 3, and therefore, since we're summing them up vertically, we're summing these areas as a function of y, dy. So let's talk about what these areas look like, right? How we can compute them, because they definitely change as a function of y. So let me just choose a different color for us. Maybe I'm going to do that in black. All right. Now let's think about what this base here, because area is basically just base times height, right? And this base, we can see that it's basically just the height of this curve. Now this curve, since we're integrating it with respect to y, we're going to change this and express it as a function of y. So what I'm just going to do is cross multiply here. That is equal to x is 1 over y. These are equivalent, right? So basically this line in black is the length, is the height of this curve in terms of y, right? If you were to flip this around like counterclockwise 90 degrees, you would see that it's basically the height of y. So this one here is just 1 over y. And now let's think about what this length here is. Well, this length, let me do it in a different color. Maybe I'll do it in red. This length over here, it basically just is the circumference, like so. It's the circumference of our cylinder, right? It's the circumference of the base. Now, the circumference of any circle is given by 2 pi r. And the radius, as we can see here, the radius goes from 0 all the way out to wherever I'm at on my y value. It's just the value of y, right? As I go upwards on my y-axis, my radius gets bigger and bigger. So for example, if I were up here, my radius would be much bigger. So it grows in accordance to my y-axis, and therefore my radius is just the value of y. And so here, this length is just 2 pi y. So therefore, I'm going to say that my area is base times height, which is equal to 1 over y times 2 pi y. Now the 1 over y cancels out with that y, which is just equal to 2 pi. Therefore, the volume is just 2 pi, right? So once we have this expression, we are ready to integrate this. And so we have that the volume is the integral from 1 to 3 of 2 pi dy. So when we integrate this, it's just going to be 2 pi y, and then evaluated from 1 to 3. Because 2 pi is a constant, so basically all we're doing is we're integrating our dy, and this is equal to 2 pi and then we're going to evaluate the boundaries, right? So 3 minus 1, and so the answer is 4 pi. Let me see if I missed anything. No, that is 4 pi, and that is the volume that we get when we revolve this area about the x-axis.